Weight Shift Control 2.1 Aerodynamics. Welcome to the fascinating realm of aerodynamics, where we unravel the unique fundamentals specific to weight shift control operations. Before we take flight into this chapter, make sure you've grasped the principles of flight and aerodynamics as outlined in the Pilot's Handbook of Aeronautical Knowledge, FAAH 8083-25. Now, let's navigate through some key aerodynamic terms. The airfoil as our protagonist, the surface-generating lift, typically the wing. Despite diverse designs, all airfoils similarly work their magic. Picture camber as the curvature of a wing's cross-section, with an upper camber on the top surface and a lower camber on the bottom. WSC airfoils can be single surfaces, ideal for slower wings, or double surfaces, akin to airplane wings, allowing for higher speeds with reduced drag. Imagine the leading edge as the charismatic front of the airfoil, and the trailing edge as its more reserved rear. The chord line is an imaginary straight line from the leading to the trailing edge. WSC airfoils boast a unique camber, with the high point shifted forward, crafting a more stable airfoil. Now, let's gaze upon the WSC wing from above. At the center is the wing root, and at each end, the wingtip. Wing chord refers to any section of the wing parallel to the wing root. The wingtip chord is where the trailing edge extends furthest rearward, a dynamic feature depending on the specific wing design. The nose angle is the angle formed by the leading edges, typically ranging from 120 degrees to 130 degrees. Sweep is the angle measured between the quarter chord line and a line perpendicular to the root chord. When viewing the wing from the rear, anhedral is the angle with wings angling down, while dihedral angles them upward. Unlike airplanes with significant dihedral for roll stability, WSC wings typically exhibit a slight anhedral and effective dihedral, a characteristic of the swept wing design. Now, let's dive into wing twist, the decrease in chord angle from the root to the tip chord, ranging from 5 degrees to 15 degrees. This twist, also known as washout, is crucial for the aerodynamic characteristics of WSC wings. The longitudinal axis is an imaginary line about which the aircraft rolls around its center of gravity, also called the roll axis. The angle of incidence is the angle formed by the root chord line of the wing and the longitudinal axis of the WSC aircraft. Unlike airplanes, the WSC angle of incidence experiences significant change in flight, as the wing rotates around the carriage hangpoint controlled by the pilot. Pitch angle is the angle the WSC wing root chord makes with the Earth's horizontal plane. Often confused with angle of attack, AOA, pitch angle is easily seen and felt, while AOA, less perceptible, is the angle between the relative wind in the wing chord line. Deck angle is the angle of the cart's wheel axles to the landing surfaces in powered parachutes. Relative wind is the direction of the airflow concerning the wing, parallel to and opposite the WSC flight path, affected by various factors like wind shear and turbulence. AOA, crucial for stability, varies along the wingspan due to wing twist. Pilots control AOA by moving the control bar forward for high angles of attack and slow speeds, and backward for low angles of attack and high speeds. The cruise AOA, the trim position of the control bar, represents the AOA and speed when flying straight in calm air. Planform refers to the shape of a wing viewed from above, ranging from larger, slower wings to smaller, faster ones. Aspect ratio, the wingspan divided by the average chord line, influences lift efficiency. Wing loading is the load per square foot of the wing, determined by dividing the total weight by the total wing area. As we explore gliding flight, soaring in descent with the engine idle or off, keep in mind glide ratios, representing horizontal travel for every vertical foot descended. Glide ratios can significantly differ between models. Strap in, and let's continue our aerodynamic adventure through the skies of weight shift control. The WSC wing maintains its airfoil shape through rigid preformed ribs called battens, supplemented by additional ribs in some double-surface wing designs. These ribs, despite their rigidity, allow the wing to be termed a flex wing for two main reasons. Firstly, the outboard leading edges of the wing are designed to flex up and back when loaded. This flexing provides load relief, reducing wing loading and increasing twists with greater weight, resulting in a smoother ride in unstable air. It also assists in initiating turns. Secondly, the wing is designed to flex as it changes and twists from side to side for turning, a concept historically known as wing warping. Unlike the traditional use of wires, The WSC aircraft achieves wing warping by shifting weight, as detailed in Chapter 3, Components and Systems. The term, flexibility, in this context does not imply a lack of rigidity but highlights the adaptability of the wing structure to enhance flight dynamics. Moving on to forces in flight, WSC experiences four primary forces: thrust, drag, lift, and weight. Thrust is the forward force generated by the powerplant or propeller, acting parallel to the longitudinal axis, relative wind, and flight path. Drag is the aerodynamic force opposing forward motion, acting in the same plane and direction as the relative wind. Lift. The aerodynamic force generated by the wing acts perpendicular to the relative wind and counters the force of gravity. Weight, on the other hand, is the force of gravity acting downward, perpendicular to the Earth. In level, steady WSC flight, these forces balance horizontally and vertically, with lift and weight forces typically exceeding thrust and drag forces. The balance ensures stability and control during flight. Dynamic pressure plays a crucial role in the aerodynamics of WSC. It is created from the velocity of the air and the air density. Understanding dynamic pressure is essential for comprehending how lift and drag respond to changes in airspeed and atmospheric conditions. Finally, lift production involves the airfoil shape and the downward deflection of airflow due to the curvature of the wing. The lift distribution in WSC wings differs from traditional elliptical distributions seen in airplane wings due to wing twists, resulting in a higher lift at the center and less at the tips. Mastering these aerodynamic principles is key to navigating the unique dynamics of weight shift control. Drag is the resistance encountered during forward motion through the air and aligns with the relative wind. There are two primary forms of aerodynamic drag: induced drag, resulting from the wing generating lift, and parasite drag, originating from the friction of air over the aircraft's various components. Understanding wingtip vortices is crucial for flight safety, as they are present in all winged aircraft, and their intensity increases with the size and weight of the aircraft. Parasite drag is influenced by the friction of air over different aircraft components. Similar to lift, it escalates with the surface area of the aircraft and significantly rises with airspeed, following the square of the velocity. Streamlining elements, like round tubes and cowlings, can be employed to reduce parasite drag, though this incurs additional costs and adds weight. The design of a WSC aircraft involves a trade-off, considering whether it is intended to be a slow-flying aircraft with a large wing, where drag is less critical, or a fast-flying one with a small wing, where drag becomes a more significant concern. Total drag, a combination of parasite and induced drag, is essential for understanding overall aerodynamic performance. Total drag increases with slow airspeeds at high angles of attack, reaches a minimum at the most efficient airspeed, and then rises as speed increases. WSC wings are capable of operating across a broad range of airspeeds. The most efficient speed, characterized by the lowest total drag, generally offers optimal performance in terms of climb rate, glide ratio, and cruise economy. However, different speeds provide advantages for climb angle and transportation speed. The specific mission and design objectives dictate the ideal balance among weight, complexity, streamlining, and drag reduction for WSC aircraft.